So let's do another example here. Let's say that we've got a small sphere, and we'll call this radius RA. And that sphere is inside of a hollow spherical shell. And the hollow spherical shell has a radius of RB on the inside and RC on the outside. And I'm going to put a charge Q1 onto the inner sphere and Q2 onto the outer sphere. So let's say that Q1 is going to be equal to minus 1.65 microcoulombs, and let's say that Q2 is going to be equal to plus 3.07 microcoulombs. Let's now say that RA is going to be equal to 1.01 centimeters. RB is going to be equal to 2.50 centimeters. RC is going to be equal to 3.10 centimeters. And so I want to know what is the electric field at several different places. So first of all, okay, and I also want to know what is the charge, surface charge on each surface of this thing. Okay, first of all, let's consider what happens if R is less than RA. That's going to be inside that smallest thing. If it's a conducting sphere inside of a conducting shell, inside the conducting sphere, the electric field is 0. Okay, done. Okay, so next, what's the charge and the charge density on the surface? So again, looking at just that, we know the charge Q1 was equal to minus 1.65 microcoulombs. So the charge density is going to be the charge divided by the area. So that'd be Q1 over 4 pi RA squared. So you plug in the numbers, minus 1.65 times 10 to the minus 6 coulombs divided by 4 pi times 1.01 times 10 to the minus 2 meters squared. Okay, so sigma comes out to be equal to a negative 1.29 times 10 to the minus 3 coulomb per square meter. Okay. All right. So now, we say, okay, if we are between, so if R is less than RB, but bigger than RA. So we've got our central sphere, and now we are looking at this region here in between the two. So now we say, we know how Gauss's law works. If we imagine a Gaussian surface right there, then EA equals enclosed charge over epsilon, and so E is going to be equal to Q enclosed over 4 pi epsilon naught R squared, or in other words, that's K sub E Q1 over R squared. And so the electric field comes out to be equal to that. Okay, so the electric field is going to be K sub E Q1 over R squared. Okay, it's going to be pointed inwards, so it'll be negative, meaning it's pointing inwards towards the center because Q1 is negative. So the question is, what is E at R equals RA? Well, what is E at R equals RA? Well, the electric field, you could just plug in here, K sub E, so you just plug in K sub E 8.99 times 10 to the 9th Newton meter squared per coulomb squared times a negative 1.65 times 10 to the minus 6 coulombs divided by 1.01 times 10 to the minus 2 meters squared. And so the electric field there would come out to be a minus 1.45 times 10 to the 8th newtons per coulomb. By the way, we know that sigma at that surface should be, well, we know that the electric field, okay, we know the electric field near the surface of a conductor, the electric field near the surface of the conductor is going to be equal to sigma over epsilon naught. So that means that sigma should be equal to E epsilon naught. If you multiply that out, what you come up with is minus 1.28 times 10 to the minus third coulomb per meter squared. You know, that's within significant figures of what we had before. Okay, so if you find E, it becomes really simple to find sigma. Okay, so now the next question is, what about if R is between RB and RC? Well, that's going to be inside that spherical shell, and if it's a conductor, the electric field is 0. So we know that. So the next question is, what about the inner surface? Well, we know that the flux, which is going to be EA, is enclosed charge over epsilon naught. Okay, if E is 0, the enclosed charge must be 0. So we know that there's minus 1.65 microcoulombs there. So that means the charge on that inner surface has to be plus 1.65 microcoulombs. So that means that I can call that QB for the charge on that inner surface has got to be 1.65 microcoulombs so that the total enclosed charge is 0. What if I want to find sigma at that point? Well, that's going to be QB over 4 pi RB squared. Okay. And so that comes out to be equal to 2.10 times 10 to the minus 4 coulomb per meter squared. By the way, so interesting thing, we know that sigma is going to be Q over A. So for spherical systems, that means it's Q over 4 pi R squared. Okay, and so if we had sigma at point A, remember that was Q over 4 pi RA squared. Well, sigma is also equal to, rather, we also know that E is sigma over epsilon naught, and so that means that the electric field would be Q over 4 pi epsilon naught RA squared, but 1 over 4 pi epsilon naught is K. And notice, both of those are really the same thing. Okay. So, again, all this stuff is self-consistent. Okay. So let's go one step. Okay. So now we have this sphere inside of this conducting spherical shell. We know that we had put a total charge on the outside here of plus 3.07 microcoulombs. But we already just figured out that's going to be split QB and QC. So QB, we just calculated before, was equal to plus 1.65 microcoulombs. Well, we know that QB plus QC is the total, so that means that QC is going to be the total minus QB. In other words, QC is going to be the 3.07 microcoulombs minus the 1.65 microcoulombs, so QC is going to be equal to 1.42 microcoulombs. So that's going to be the charge on the outside. Okay. Well, if we got the charge on the outside, sigma c, the charge density in the outside, would be QC over 4 pi RC squared. Okay, so you plug in the numbers, that comes out to be 1.18 times 10 to the minus 4 coulomb per meter squared. So the next question is, well, what if I pick a point out here that is a distance of 10 centimeters away? Well, draw a Gaussian surface there. And so we know that EA is enclosed charge over epsilon. So E is basically going to be equal to enclosed charge over 4 pi r squared epsilon, where that's my r. Okay, so the enclosed charge is going to be QA plus QB. So QA plus QB over 4 pi r squared epsilon. Well, what is QA plus QB? QA plus QB is going to be equal to QC. Okay, and so QC, it turns out to be the 1.42 microcoulombs. So if we plug in all the numbers, the electric field, okay, going to be K QC over r squared, so 8.99 times 10 to the 9th Newton meter squared per coulomb squared times the 1.42 times 10 to the minus 6 coulombs divided by 0.1 meter squared. So the electric field at 10 centimeters is going to be equal to 1.28 times 10 to the 6 newtons per coulomb. Okay, so there is how you do that problem of a conducting sphere embedded inside a conducting spherical shell.